I think we lost Professor Gokhale's audio. I'm trying to reconnect to him. Okay, here he is.
Hello, Jamit. I think I was kicked out due to some technical glitch. Yeah, nice to be back again. So let us quickly continue with the points which I was discussing. So I was making a quick mention about various decision tree algorithms, and popular among these algorithms are CART. CART is basically the classification and regression tree algorithm, which uses the Gini index mechanism. And we also have got ID3, C4.5, the popular classifier 4.5, and modified version of that is C5.0. All the three of them use the entropy based mechanism for determining the splitting nodes. And all these four different decision tree algorithms work out on categorical data as well as continuous data, right? Uh, Decision tree is a pretty very good approach for classification. But what people have found is rather than using a single decision tree, why can't we have a bunch of this decision tree to create a forest? And that is what is typically called as a random forest implementation. And this random forest implementation and the decision tree implementations are pretty very popular for a variety of classification algorithms like risk analysis and stuff like that. So let me quickly tell you what is this random forest approach. This is called as an ensemble learning technique. And here it uses the outcomes of multiple classification mechanisms, combines them together to make a much more well informed, robust decision. So, how does it work? It uses the data set, and that particular data set would have multiple features. A few selected features would be used, and a decision tree would be created. Let us call this as tree 1. Similarly, another subset of features is extracted from the data set and an alternate tree is created, tree 2 and tree 3 and tree 4. So this way multiple trees are created. All of them are decision trees. And now I have a collection of decision trees which can work simultaneously for classification. Obviously, each of the decision tree would produce its own outcome, its own class labels. So I combine all these outputs from each of the tree into deciding what is the final class. And the approach I'm going to use out over here is what is called as majority voting. So as shown in the picture here, decision tree 1 and tree 4, both of them give a class C as the outcome, whereas 2 and 3 give class D and class B. So I can now very clearly say that the majority of the outcomes is class C, because of which the final class is also class C. And incidentally, in practical implementations, people typically create not just 3 4 decision trees. They create something like maybe about 5,000 to 10,000 decision trees. All of them work in parallel, right? It's a pretty very robust approach, and random forest is a very very popular algorithm, and its application are into risk evaluation, into customer segmentation, attrition predictions, and so on and so forth. Right? So all these are classic examples where decision trees can be used. Then we will move on to one very very interesting, let's say, pattern recognizer or a classifier, and this is called a neural network. And let us quickly see how this neural network works. And I just will very quickly run through a few slides. Neural networks, or ANNs as they are very commonly called, come under the category of supervised learning algorithms, and it is primarily meant for classification. So remember, now supervised means what you should have already had with you a bunch of training records which are already pre-classified. And the way this neural network functions is primarily modeled on the lines of how the human brain learns about any aspect. So a similar type of a learning mechanism is what is implemented as part and parcel of artificial neural network. And the best part of how this neural network really performs better is in this massive interconnected network of these computational elements called as the neuron implementations. So what goes inside? We have one element, the so-called computation element. We call this as a perceptron, quite similar to the perceptron cell, the angiom cells, and the dendrites and stuff like that as part and parcel of our human brain. So we have a perceptron, and the perceptron is modeled as a very simple summation function over a bunch of inputs. And what are these inputs? Inputs are all your features. Now, for example, the first feature could be, does the employee work in an MNC? Yes or no. Is the employee having salary more than 10 lakhs? Yes or no. Has the employee taken any loan? Yes or no. How many times his credit card was not funded properly? That counts. So all these inputs typically will be going inside, appropriately managed by some weighting function. This weighting function tells which of this input is more prominent compared to the others. And all of them go in out over here. They get mashed up in a small compute engine, and it just generates an output which is actually applied onto a very simple decision maker here. So what is this decision maker doing? The realization of this computation will be identifying whether the class output class will be true or false, yes or no, or whatever it is, right? So that is the outcome here. Second thing what I do is something like this, taking this outcome, simply because these outcomes pertain to some inputs which are already pre-classified. I check out whether this outcome is exactly matching with the class label already given to me. If so, I say that the error is not there. If there is some error, I will estimate this sort of an error. Using this particular error, I have a function which alters these weights, changes the weights. And once I change the weights, next time using the same inputs, because the weights are different, the computation that happens out over here, the summation, etc., would be different, because of which, once again, this particular activation function could probably generate an output which might be closer to the true output. So this is what is called as a forward flow of the data, and I estimate the error, use the error as a mechanism to alter the weights. So this is what is called as a single perceptron model. And a neural network typically is created by using a bunch of such perceptrons and putting all of these perceptrons in a layer. So layered set of perceptrons will give me what is also what we call as a neural network. So let me quickly show you how the artificial neural network looks like. So the artificial neural network has all these nodes. Each of these computational element is called as a node, and these nodes are set up as layers: the input layer, the hidden layer or the intermediate layer, and the output layer. And because it is having multiple such nodes, we call this as a multi-layer perceptron model, MLP model of a perceptrons. So this is how it typically looks like. So here is my income as an input, marital status as an input, owns house as an input. These all inputs trigger the input nodes, and the input nodes are connected to the intermediate hidden nodes, as we call them. And you have got a whole bunch of weights out over here on these limbs, on these linkages, and that particular weights will decide which of the factor is more prominent, which of the factor is not so very prominent, and that will decide what exactly will be the computation that is carried out in the hidden layer as well as in the output layer. The output layer typically will give me an output which says the car loan can be given, the sell policy is no, whether I can sell an insurance premium or not. No, I cannot probably sell an insurance premium, stuff like that. So it can be used primarily to give multiple set of outcomes based out on these particular inputs. And please once again notice, the outputs we are taken, we estimate the error. The error is typically used to as a feedback mechanism to alter the weights here, then weights here and weights here. So you just do what we call as back propagation. Back propagation is a mechanism wherein we take the error, define appropriate functions which try to change the weights across the several layers. So this is how your multi-layer perceptron typically works. Applications, risk assessment, disease prediction, very popular for cancer detection and stuff like that. Vendor classification, I have got multiple suppliers supplying raw material and components to me. I can use this neural network to classify my vendors. Document classification, let's say I have a document, I want to categorize whether this particular document pertains to a business document, or whether it typically talks about sports, or whether it talks about finance, whether it talks about politics, whether it talks about entertainment. I can typically look at a paragraph of text and then try to identify to which category does this particular paragraph belong to. Once again, a very popular application of neural networks. Image segmentation. So you have got an image, and out of this image, I would like to extract relevant components of the image so that my focus could be only on that particular component, right? Eliminating the rest of the things. So extract the features of each and every component, then segment my image. So once again, done by neural networks. And voice and image recognition. So for example, as I speak, I can identify what I'm speaking. Similarly, I can also identify who is the speaker. So both these two can be done as a neural network application. Right? So these are various applications which are very popular. Let me quickly extend this concept to what we call as deep learning. Deep learning essentially is an extension of neural networks where you increase the number of layers. And by increasing the number of layers, you not only improve the recognition accuracy, but you can also do a lot of activity on the features, right? You can enrich the features before you give it to your learning, before you give it to a classification engine. And all this can be done as part and parcel of an integrated approach of multiple layers of a neural network, right? So that is what is called as a deep learning model. Okay, so the deep learning model goes something like this. In a normal case, you could have taken the input data, then you will typically have an alternate offline approach to extract the features which are fed to the classification engine. And this classification engine will tell me whether the image is pertaining to a car or not a car. Whereas in deep learning, even the feature extraction part is also implemented as a bunch of additional add-on layers of neural network, right? So input is taken directly, features are extracted out over here, and this extracted features are fed into the classification engine, which typically tells you as an output whether it is a car or a not a car. So deep learning models are extended forms of neural networks with large number of layers. Typically, it can go to some 30 layers and 50 layers and even 100, 200 layers also, or there, depending upon uh, how you are actually learning bit by bit, reinforcing your learnings bit by bit, and ultimately provide a very clean set of features to the classification engine so that the classification engine will not make any error. So that is implemented through what are called as the convolutional neural network. So let me not get into the details of that, but the way it goes is something like this. Whatever is the input, you take the input, take a small part of the input, and then prepare maybe a multi-layer neural network to handle that small part of that particular input, and use the same model, run over the remaining parts of the input, and you do this through a process of what we call as convolution. Convolution is a very popular let's say activity in digital signal processing. So you apply that primarily to boost up the features which are to be recognized, make the main feature stand out so that my recognizer, my classifier, will not make much of an error. So that is basically the central theme for convolutional neural networks. When you come down to implementation, let me just go through two more slides. How do you implement your machine learning algorithms? First, you need to write down appropriate code for your model. So whatever model you have created, that has to be implemented as a computational model. So you use programming languages like Python or R or etc. Any language which is having a good support of libraries, you use those languages. Then you can also probably use additional frameworks. For example, for Python, you use Keras or TensorFlow. These sort of uh, frameworks and modules are there, and they are pretty very aggressive. It reduces your burden of writing down complex code. And if your data which you are typically handling is extremely large, you can now think about a cloud based implementation. So your data is put up onto the cloud. So will be your machine learning model. So your machine learning model could work out on some cloud instance, and that particular cloud instance will host your ML model as an application. So once again, you have got AWS, uh, Google Cloud, and Azure, and all these big players are offering a bunch of infrastructure and associated platform and specific tools so as to uh, create your applications, create an appliance, and then also deploy it, host it for your end users. So they have created a whole bunch of infrastructure to make these machine learning workloads possible, to make these sort of applications easily accessible to the end users. Okay, one very nice way of doing this is through Amazon SageMaker. A lot of people also create what are called as containerized applications. So they come up with containerized design. They use Docker containers or they use Kubernetes, and then create containerized applications for your classifiers or whatever it might be, the machine learning uh, application, and they integrate that into a CI/CD pipeline. Remember, uh, I just cannot prepare one model and sit idle. I have to prepare a model. Once again, the moment I acquire new data, I have to rework on the model. I have to do this operation as a continuous activity. That is the reason why CI/CD pipeline is also very important and effective in such a use case. Okay, so that is the complete pipeline. You capture the data. After that, you clean the data so that the data is enriched, and then you curate the data, put up some proper labels and standardize them, normalize them, homogenize them, harmonize them. You put up all such things and then ensure the fact that the data is nice and clean. And then wherever required, you also annotate the data. Finally, create the ML model, and this particular ML model will be properly trained and typically tested before it is deployed. Okay, so that is the overall uh, pipeline for deployment of machine learning applications. That is a quick summary of what we mean by models, machine learning models, and some of the standard popular machine learning models associated applications have been discussed. Thank you very much. And in case you have any questions, kindly feel free. I would like to see some questions coming up on the chat box. Thank you, Jamit. Over to you. Over to you, Jamit.
Yeah, thank you, Professor Gokhale, for giving us walking us through the AI/ML concepts. Thank you very much.